Thanks to Brilliant for sponsoring today's video.
So recently I made a video about the dimensions in which the cross product exists. And well, today I'd like to look at a more restricted version of the cross product. Well, in some ways more restricted, but in some ways we're making some or taking away some of the assumptions. Okay, so let's see what we have here. Oh yeah, and by the way, this is about the role of the triple cross product identity in the definition of the cross product. So before we really get into it, if you recall from that previous video, the cross product existed in 1 dimension, 3 dimensions, and 7 dimensions. The one-dimensional version was not very interesting. It was just the zero product. And then, well, in the 3-dimensional cross product, it satisfies something called the Jacobi identity from Lie algebras. The 7-dimensional cross product does not. And this triple product identity is related to the Jacobi identity. And what we're doing here is based on a paper from 1969 by F. Callahan. Okay, so let's see what we have. Suppose we've got a product, which I'll call star at the moment, and it's a product on Rn. So that means it takes two n-dimensional vectors and you multiply them and get a new n-dimensional vector. And here we're going to assume that n is bigger than or equal to 2. You could look at the case when n is equal to 1, but I think everything would collapse to just the zero product. And then let's also suppose this product satisfies this triple product identity. So A star B star C is equal to A dot C in the B direction minus B dot C in the A direction. But that's the only thing we're assuming that this product satisfies. We're not assuming that it is linear or how it deals with scalars or anything else. We're only assuming it satisfies this one identity. Now, of course, if you know something about the cross product satisfies this identity. But here, like I said, this is an abstracted product that satisfies this single identity. And the fact that it satisfies this single identity allows us to prove a couple of things about this product. First of all, it's bilinear. So by bilinear, it means you've got some sort of distributive rule and way to deal with scalars in the first entry and the second entry. Here you have it in the first entry, and here you have it in the second entry. This product is also alternating, or sometimes called skew symmetric or anti-commutative. That means if you switch the order of the product, you pick up a minus sign. So in other words, A star B is negative B star A. And maybe the most surprising thing here is that any product that satisfies this identity only exists in 3 dimensions. So this restricts n to be equal to 3. Okay, so let's see how we might prove this. We're going to start with a lemma. And this lemma looks like it's towards this anti-commutative property, but it's actually going to be used to prove the linearity as well. So what we'll start showing is that for vectors a and b and Rn, we have A star B is equal to B star negative A. So observe that I don't know linearity here, so I can't bring this minus sign out. Okay, well, let's maybe just like start with this identity here, and let's rewrite this identity here a little bit. So let's look at B star negative A, and then we're going to star that with C. So in other words, we're applying our, well, only identity that we know that holds, where A is replaced with B is replaced with negative A, and C, well, C is the same. Okay, so this is going to be equal to B dot C, and this is going to be in the negative A direction, and then minus negative A dot C, and that is in the B direction. But now we're in this world with the dot product. We can use, dot product identities. And that'll allow us to write this as A dot C in the B direction minus B dot C in the A direction. But let's observe that that's exactly this right here. So in other words, this is equal to A star B star C. So look at what we did here. We took this object, this B star minus A, and if we star that into C, we get the same result as doing A star B into C. Now, that does not tell us that that we're done here, because you can't like cancel the C from both sides. But what it does say is that this holds for all, vectors C. So let's write that down here. So for all vectors C in Rn, we have, let's write it like this. A star B star C is equal to B star minus A star C. Okay, nice. And now here's the trick. We're going to take a new vector, and that new vector, well, it's got to have some certain property. So let's take any D inside of Rn such that D and C are orthogonal. So that means they're perpendicular, or in other words, their dot product is equal to 0. That's a defining property of orthogonality. So we'll say here C dot D must be equal to 0, and I'll just put here that C and D are orthogonal. And now let's look at the following object. So we'll have A star B star C, and then we're going to star that into D. Okay, nice. So now pulling this apart, where now we're going to apply this rule again, but now the role of A is being played by A star B, the role of B is being played by C, and the role of C is being played by D. So it's just like a substitution game here. So this is going to give us A star B dotted with D, and that's occurring in the C direction. And then from that, we need to subtract C star D, and that's occurring in the A star B direction. But now let's observe that we made this assumption that C and D were orthogonal, so that means C dot D is 0. So that means this bit is just gone. So we don't need that term at all. Okay, so now let's use this rule right here to switch the A and the B and pick up this minus A here. So let's see. That's going to give us B star minus A. We're going to star that into C and then star that whole thing into D. And let's see what we get out of that. So applying the rule again, we'll get B star minus A dotted into D in the C direction, and then minus C dot D again in the B star minus A direction. But again, C dot D is equal to 0, so this is 0. We don't need that right there. But that sets up an equality of these two vectors. So we've got these two vectors in the C direction. But since they're both in the C direction, we can just pull off their, scalar multiples, and their scalar multiples must be equal. And notice that we have now A star B dot D must be equal to B star minus A dot D. But notice that this is really holding for any vector D. And that's because, well, this was for arbitrary C, and then on top of the arbitrary C, we took an arbitrary D that was perpendicular to it. So we might as well have just like chosen the D first and chosen the C second. So this is for all D inside of Rn. But look at what we've got. For all vectors D inside of Rn, we're dotting something with it and getting the same thing as dotting something else with it. But there's a property of the dot product that, in fact, allows us to cancel the D from both sides, if you will, if an equation like this holds for all vectors D. So that gives us our result. We have A star B is equal to B star minus A. So let's move on to our second lemma.
Hey there, I'd like to take a minute to talk about today's sponsor, Brilliant.org. While watching my videos is a great place to start, You get more out of learning by doing, and that's why I highly recommend you sharpen your skills with Brilliant. Brilliant is where you learn by doing, with thousands of interactive lessons in math, data analysis, programming, and AI that are individually matched to your unique level. Each lesson comes with hands on problem solving so that you can truly learn the material. It's been proven to help you learn 6 times more effectively than just watching videos. Content is designed by an award winning team from MIT, Caltech, Duke, Microsoft, Google, and more. You'll find yourself learning real life problem solving skills instead of memorizing equations. Brilliant can also be easily incorporated into your daily activities, with fun lessons that you can do on your phone, tablet, or computer in just minutes a day. Check out the course library. They have lessons on vectors to help you learn the basics. You'll be comfortable with basic vector equations like scaling, transformations, polar coordinates, and the dot product in no time, and will develop comfort solving complex problems in multidimensional spaces. But we're scientists here, so don't take my word for it. You should test it for yourself. Treat yourself to a unique hands-on experience by going to brilliant.org/michaelpenn for a 30-day free trial and 20% off your annual subscription. Thanks once again to Brilliant for sponsoring today's video.
Now moving on to our second lemma, let's suppose that A star B decomposes as alpha times U star B plus beta times V star B. And then if that occurs, then A is a linear combination of U and V. So it's alpha U plus beta V. So this is like a weird kind of thing here. This is almost like linearity in reverse. Okay, so let's see how we might prove this. So let's start with this equation right here, the given, and let's maybe replace the b with a minus b. So that's going to give us this. We'll have alpha star minus b is equal to alpha u star minus b plus beta and then v star minus b. Okay, but now we can apply lemma 1 to like switch the, well, minus sign on the b and the order of the starring. So let's do that. So let's say here, this is from lemma number 1, which I left on the board there. So this is going to give us a new equation. B star A is equal to alpha B star U plus beta B star V. Okay, so that's pretty nice. And now we're going to make a substitution here, and our substitution will be to replace B with B star C. So let's do that. So here we're going to replace, like I said, B gets replaced with B star C. And I guess I should say here that it's kind of important to choose B and C to be linearly independent. So in other words, B is not parallel to C. If you're just dealing with two vectors here, linear dependence or independence can just be phrased in terms of parallelness. Okay, good. So let's see what that leaves us with. So we'll have B star C star A is equal to alpha, and then we have B star C star U, and then plus beta, and then we have B star C star V. So something like that. But now we're going to use the triple product identity to decompose everything there. So let's do that. So for this first term, we'll have B star A in the C direction minus A star C in the B direction. Okay, so that's from this left-hand side. And then from the right-hand side, we'll have alpha times, and so we'll have B star U in the C direction, and then minus C dot U in the B direction. Okay, so something like that. And then we'll have a beta term as well. So let's see, that'll be plus a beta. And then we'll have B dot V in the C direction. And then after that, minus C dot V in the B direction. So something like that. Okay, nice. But now let's observe what we can do here is set each of the coefficients of b and c equal to each other. And that's because b and c are linearly independent. So let's do that here. So the coefficients of vector b on both sides of the equation give us the following. So over here, we're going to have a minus a dot c. And then over here, we're going to have what? So it's going to be minus alpha c dot u, and then minus beta, and then c dot v in the b direction. Oh, but we're just extracting the b direction here. Okay, but now let's rewrite this a little bit. Observe that we can cancel all the minus signs, and then we'll be left with a dotted in with c is equal to alpha u plus beta v dotted in with c. And that's, well, that's because here what we did was just use a distributive rule, or the linearity of the dot product on the right-hand side. But now observe that c was essentially chosen arbitrarily just to not be parallel to b. And then we're dotting two different vectors into this arbitrarily chosen vector and getting the same thing. But again, by properties of the dot product that we used in the previous lemma, that tells us that this vector A is equal to this decomposition right here, alpha u plus beta v. But that's exactly where we wanted to land. Okay, let's move on. Now we're moving on to our next result, which is that this star is bilinear. And so this is the first part of the, well, theorem. I didn't write theorem up there, but the theorem that we are proving. Okay, so let's see how we might do this. So let's take a linear combination. Let's take alpha A plus beta B, and we're going to star that into C. And then we're going to star that whole thing into D. And then we're going to decompose this with the triple cross product, because, or the triple product identity, because, well, that's what we have here, a triple product. Okay, so what's that going to leave us with? So let's see, we're going to have alpha A plus beta B, and then that's going to be dotted into D, and that's going to be in the C direction. And then we'll have minus C dot D, and that's in the alpha A plus beta B direction. But now let's pull that apart a little bit. So let's pull out all of the coefficients of alpha. So if we have alpha, then we're going to have A dot D, and that's in the C direction. And then over here, what are we going to have? Minus C dot D, and that's in the A direction. And then we'll also pull out the coefficient of beta. And pulling out the coefficient of beta, we'll have, let's see, B dot D in the C direction minus another C dot D in the B direction. So something like that. But now we can apply the triple product identity twice to these two things that are in parentheses. And that'll leave us with, for this first one, alpha, and then A star C star D, and then beta, and then over here we'll have B star C star D. Okay, so that's looking good. But now let's see what we've got here. So we're starring all of this with D, and that's allowing us to split this into two pieces. So that thing starred with D, and then this thing right here starred with D. But now we can apply lemma 2 to pull the starring with D out of this, which is kind of what lemma 2 is allowing us to do here. So in other words, we have alpha A plus beta B starred with C is equal to alpha A star C from this first term plus beta B star C from this second term. But that's linearity in the first component. Now, maybe I'll leave linearity in the second component as a bit of a homework exercise because it's very, very similar. Okay, so now let's prove the anti-commutativity or the skew symmetry or alternatingness of this star. Now we're going to prove the anti-commutativity of star, but this is going to be super quick. So we're going to start here with A star B, which we know is equal to B star minus A. Oh, but now we can apply the linearity in the second entry just to bring that minus sign out, and we have minus B star A. Okay, so there we have its anti-commutative. Oh, but that means all that's left is to show that n is equal to 3. So let's do that now. So now we're going to jump into the most surprising fact here, and that is that the dimension must be equal to 3. Okay, so let's start with this. We know that the dimension is bigger than or equal to 2, so that means we can take two orthogonal unit vectors. So I'll call them E1 and E2. So E1 and E2 in Rn, and like I said, they're going to be orthogonal, and they're also going to be unit vectors. Okay, great. And now let's set E3 equal to E1 star E2. So you might immediately want to say that it's perpendicular, but that's only true for the cross product. We don't know that this is yet the cross product because we don't even know if we're in R3 yet. Okay, so that's going to be our first little bit of a claim inside of this proof. So let's put that claim right here. So E1 is orthogonal to E3 and E2 is orthogonal to E3. Okay, so let's see how that goes. So let's observe that 0 is equal to E3 star E3. Well, why is E3 star E3 equal to 0? Well, that comes from the anti-commutativity. Notice we could switch the E3 with the E3 and we pick up a minus sign. But that means we've got a vector is equal to its negative, but the only vector that's equal to its negative is 0. Okay, so now let's write maybe this first E3 as E1 star E2. So we have E1 star E2, and then we're starring that into E3. And now we're ready to use the triple product identity. So that's going to give us E1 dot E3, and that's occurring in the E2 direction, minus we've got an E2 dot an E3, and that's occurring in the E1 direction. But notice we've got what's essentially a linear combination of E1 and E2 equals 0, but the orthogonality implies these are linearly independent, but that means that the coefficients are 0. But those coefficients are exactly what we need for orthogonality. In other words, we know E1 dot E3 is 0, and we know E2 dot E3 is also equal to 0. So now I guess we probably need to check that E3 is not the 0 vector. And along the way, we'll get some other nice properties. So maybe let's put this under like an observation or something that we're noticing. So let's do E3 star E1, which is obviously E1 star E2 star E1, based off the definition of E3. And now let's use the triple product identity here. So that's going to give us E1 dot E1 in the E2 direction, and then minus E2 dot E1 in the E1 direction. But we know E2 dot E1 is equal to 0 because those are orthogonal. Then we know E1 dot E1 is 1, so this is E2, but that's not the 0 vector. So here we have E3 star E1 is equal to E2, not the 0 vector, but this implies that E3 is not the 0 vector because anything starred with the 0 vector is obviously equal to the 0 vector. I think that's pretty clear. And then maybe like also, which I'll leave as a little exercise or a little homework, you can check the following. E2 star E3 is equal to E1. So that gives us this like nice little loop in this star operation. So E1 stars to E2, E2 stars to E3, and E3 stars to E1. And furthermore, these are all orthogonal. And then we can also check that E3 is a unit vector. So let's do that. And then after that, we'll see that we've got a version of the cross product living inside of our structure. So let's do E1. So let's write this as E2 star E3. But now we can take this E2 and write it as E3 star E1. So we have E3 star E1 star E3, and then use the triple product identity on that. So that'll give us E3 dot E3 in the E1 direction, and then minus E1 dot E3 in the E3 direction. But of course, we know that E1 dot E3 is 0, so that goes to 0. And then we've got E1 is E3 dot E3 in the E1 direction, but that tells us that E3 dotted with itself must be equal to 1, meaning that we have a unit vector. Okay, so let's summarize what we have so far, and then we'll finish this proof off. Okay, so what we've done so far is shown that we've got a copy of the three-dimensional cross product inside of our n-dimensional star product. And that's given by this vector subspace, which is spanned by E1, E2, and E3. If you're more comfortable with the I, J, K vectors, you know, maybe E1 is I, E2 is J, and E3 is K. And now what we want to show is that, well, n cannot be any larger than 3. It has to be exactly equal to 3. And how can we do this? Well, let's suppose that u is inside of Rn and it is perpendicular or orthogonal to E1 and E2. So let's write that down. So orthogonal to E1 and E2. Now, observe if n is equal to 3, then that means that u should be equal to E3. But if n is bigger than 3, there are lots of different choices for u because, you know, we've got different directions to go in. Okay, so now let's make a calculation. So we're going to do the following. Let's do E3 starred with u. But that's going to give us E1 star E2 starred with u. And now we can use the triple product identity on this. So that's going to get E1 dot u, and that's occurring in the E2 direction. And then we'll have minus E2 dot u, and that's occurring in the E1 direction. But now let's observe that those are both equal to 0, because we're assuming that E1 is perpendicular or orthogonal to each of those. So that means this is equal to 0 and this is equal to 0, making this whole linear combination equal to the 0 vector. Okay, but now we can do the following. Notice that 0 is going to be equal to E3 star u starred with another u. Well, that's because this thing right here we just showed was equal to the 0 vector. Now let's use the triple product identity on this without the decomposition of E3. So that's going to give us E3 dot u in the u direction minus u dot u in the E3 direction. And well, I guess while we're at it, let's assume that this is orthogonal unit vector. So sorry, an orthogonal unit vector, just to make everything nice. So that means we can replace this u dot u with the number 1, and then we can, well, in some ways solve. So observe that we have our vector E3 is equal to E3 dot u in the u direction. But this equation right here tells us that u is parallel to E3. In other words, any vector u that's orthogonal to E1 and E2 must be parallel to E3. But that condition is strong enough to mean that we only have a three-dimensional space. Otherwise, we would have more vectors that are not parallel to E3 that are orthogonal to both E1 and E2. And that's a good place to stop.